Hello everyone, this is Hamada Rizk. Today I'm going to share with you OmniCells, cross-device cellular-based indoor location tracking using deep neural networks. This is a joint work with my colleague Mustafa Abbas and my advisor Professor Mustafa Yusuf. As people spend most of their time indoors, recent years have witnessed an ever-growing demand for accurate and ubiquitous indoor positioning systems in many applications, including location tracking, navigation in big malls, crowd detection, and even emergency services. The criteria for the required localization system is to be accurate enough for indoor settings, ubiquitous, where the system is able to work anywhere with the same efficiency and on any user device, high-end or low-end phone, easy to deploy, and finally, comes with low cost, and usually this cost is due to the infrastructure setup or maintenance. The state-of-the-art localization systems can be broadly categorized into, first, Wi-Fi based systems. Despite Wi-Fi is widely adopted for indoor localization, the accuracy of the Wi-Fi based systems usually depends on the Wi-Fi coverage, which may not be available in every indoor environment, especially in developing countries. Wi-Fi support. Not all cell phones are equipped with Wi-Fi chips, especially low-end phones, and this affects the widespread adoption of Wi-Fi based systems. Finally, infrastructure changes by replacing and upgrading access points. Usually, this adds additional cost for recalibrating the running systems. On the other hand, we have sensor-based systems. These systems leverage the smartphone's inertial sensors such as accelerometer, gyroscope, compass to estimate the user location. The main problem with these techniques is the noise in the sensor measurements, yielding error accumulating quickly over time. Additionally, these systems require high-end phones to work, limiting their ubiquity. Another line of research suggests cellular-based systems due to their advantages that make them more attractive than their counterparts. For example, cellular coverage far exceeds the coverage of Wi-Fi networks as cell towers are dispersed with high density across the inhabited world. Secondly, it is supported by any cell phone by definition, including high-end phones and low-end phones. Then, it also consumes zero extra energy in addition to the normal operation of the phone. Finally, unlike Wi-Fi based systems, cellular systems has rare infrastructure changes due to the consequent significant expenses of this process when performed frequently. These advantages motivate us to use cellular technology in our localization. So the basic idea is to use fingerprinting technique, which consists of an offline calibration phase during which the cellular signals are captured at predefined reference points in the area of interest and then stored in a fingerprint database, which is then leveraged to train a localization model. This model can be then used to estimate the user location in the online phase. Based on this approach, the received signal strengths are used to characterize the corresponding locations. But what will happen at the online stage of the system if the user has a different phone than the one used in the fingerprinting? Does the system accuracy will remain consistent? To answer this question, we have to figure out the effect of device heterogeneity on the received signal strength. To do so, we carried out an experiment by collecting cellular measurements using two phones running simultaneously over all different reference points of our testbed. As we can see from the heat maps, device heterogeneity leads to a remarkable variation in the received signal strengths, which in turn significantly deteriorates the system performance as we will see in the evaluation section. So the major challenge here is to find a robust and discriminative features across different devices instead of the raw RSS. Otherwise, we will have to train a specific model for every possible device in the market, which is not possible. So we propose OmniCells, which can map the input cellular received signal strengths to a device invariant feature space, combining classical and deep learning based feature extraction. We also deployed OmniCells in two different realistic test beds, and we obtained a consistent accuracy across different and unseen phones. So our agenda for today includes a discussion of the different modules of OmniCells. Then we will go over the evaluation section, which will include a demo of how the system behaves in one of our test beds. Finally, we will conclude our presentation and give some directions for the future work. This is the architecture of the OmniCell systems, and we will go over the different modules one by one. The system is initiated at the offline stage by collecting data at predefined reference points in the area of interest using a fingerprinting collector app which is installed on the user's phone. The app scans for the cell towers here in the area of interest, and each scan represents cell information from up to 7 cell towers, including cell tower ID and the received signal strength. The collected scans are then fed to a preprocessor module. This module, as shown in the figure, extends the length of the original scan from only 7 entries or less to the length of all detectable towers in the area of interest. And non-heard cell towers are assigned 0 SU. Then this module increases the amount of training data for enabling the effective use of deep learning using different data augmentation methods, including sampling, generative model, noise injection methods. Please refer to the paper for more information about these methods. The feature extractor module is our main module, which hopefully extracts device invariant features. We have two feature extractor methods, the difference and the encoder. Firstly, to show how the difference method works, let us start by assuming that we have 3 cell towers covering the area of interest and transmit a signal with this amplitude 5, 7, and 12 ASU respectively. And these signals are received simultaneously by two different phones with different amplitudes depending on the added component by the phone hardware. And to eliminate this added component, we apply the difference operator on each pair of RSS detected by the phone. For example, 7 minus 9 is 2, and 7 minus 14 is 7, and 9 minus 14 is 5. And we will get the same values for this phone as well. So the two phones become equal in the new space, which is a difference space. The second feature extraction method depends on the autoencoder network, which consists of two parts, the encoder part and the decoder part. The encoder encodes and compresses the input into a lower dimension Z, from which the decoder reconstructs the original input form. So this network is trained to represent the main features in the latent space. We have a modified version of this network, which we call the encoder-decoder model. To describe how it works, assume that the sensed RSS includes two components, the original transmitted value Z and the device added component epsilon, which may vary from phone to another. And to allow the network to learn Z, we train the network using data collected by an arbitrary source phone to reconstruct data collected at the same time and same location by different phone. This forces the network to learn generic phone invariant representation in the latent space, which may lead to enable device transparent localization. In case of only few phones are available in the offline phase, the training process can operate as shown in this figure. We have data collected by 3 different phones simultaneously. So OmniCells employs multitask learning, which aims to optimize the encoder-decoder model with respect to multiple objectives. We train the network with data collected by an arbitrary source phone, yeah, this one, and the model is then asked to reconstruct data collected by the 2 different target devices. Each device of the target devices has its own decoder stacked over the encoder. Therefore, the network is trained to minimize the reconstruction loss of each target device. And this ensures that the network learns more general encoder, which by extension more general latent representation to accommodate the diversity between different devices. OmniCells can also operate when only a single phone is available during the offline phase. Some work in the literature model the device effect on the received signal strength as an added random noise. So OmniCells leverages and emulates this effect by adding a Gaussian noise to the original signal, which leads to a distorted version of the input. This version is then used to train a model to reconstruct the noise-free version using a denoising autoencoder. So this network is forced to learn only the salient features of the input at the latent space. The extracted features obtained from this module are a combination of the encoded latent features and the difference features. These features are then used to localize the user. Now we have the model builder. This module is responsible for training a deep localization model, which is chosen to be a fully connected layer due to its representational learning ability. The input of this network is our features. The output is a number of neurons corresponding to the number of reference points surveyed at the data collection time. This network is trained to operate as a multinomial classifier by leveraging a softmax function in the output layer. This leads to a probability distribution over the reference points given an input scan. These probabilities will further used in the online stage. To increase the model robustness against overfitting, we adopt dropout regularization, which stochastically exclude some neurons from each layer and their corresponding connection in the training. In effect, it prevents the neurons from co-relying on each other, making the model more robust to unseen data and less likely to overfit. Now, the online location predictor. During the online phase, the ROA received signal strength scan is fed to the feature extractor module to extract features which are then forwarded to the trained localization model to get the probability of each reference point to be the user location given that scan. However, reporting the point with maximum probability, even with very accurate model, leads to spaced out or discrete estimations which negatively affects the user experience. So OmniCells estimates the user location as the center of mass of all reference points weighted by their corresponding probabilities. This leads to a user tracking in the continuous space. Additionally, outlier estimations are ignored to maintain consistency of the user trace. Finally, the system performance is further enhanced by map matching. Now, we will move to the evaluation section. OmniCells is deployed in two real-world test beds. The first one is the big one, which spans a floor of our university campus, with an area of 629 meters square, containing several labs and furniture. The second one is an apartment of 132 meters square. To facilitate the ground truth profiling, the same data collection app runs synchronously on all phones, with one phone controls the start and stop of the collection on all phones. For evaluation purpose, Google Pixel XL and DTE ZTE Z Blade 7 are dedicated as holdout testing devices. Here, we investigate the effect of the main module and parameters on the system performance. Firstly, we study dropout regularization. As shown in the figure, using dropout regularization, a dropout percentage of 15% enhances the median accuracy by 38% compared to the case with no dropout is used. Beyond 15% dropout, the error increases again as the model tends to underfit the training data. As discussed earlier, the feature extractor consists of two submodules, the difference and the encoder. This box plot shows the effect of each method separately on the performance of OmniCells. The figure confirms that the combination of the two proposed methods gives an improvement in the performance compared to using the raw RSS or each individual method. Here, we show how the system performs when tested with every individual phone. As can be seen from the figure, OmniCells provide consistent median localization error for the different phones. On the other hand, the unseen phones shows massive error in the baseline when the raw RSS is used. These results confirms the robustness of the system when tested with different unseen devices. Here, we study the effect of using multiple phones mode as compared to single phone mode. The multiple phone mode, as expected, the purple curve, gives better accuracy due to the use of multiple decoders, which leads to more general features. Nevertheless, both modes provide consistent tracking for unseen phones. Here, we compare OmniCells to 5 other systems. 3 of them are cellular-based localization systems that leverage the raw RSS to identify the user location. Each system builds its own classifier, while the remaining 2 are device invariant localization systems that use either transformation models or signal strength ratios. As shown here in these CDFs, OmniCells, the purple curve, gives an improvement in the performance in both test beds compared to the other system, as it handled the device heterogeneity by transforming the raw RSS into more general space where the device-specific components are reduced. We also compare the accuracy of OmniCells to the device invariant-based systems. The CDFs show the superiority of OmniCells. This can be explained by noting that the compared schemes assume a linear mapping between measurements from different phones, which is not generally justified. OmniCells, on the other hand, uses deep learning to learn the latent features which lead to a better accuracy. Here, we show a real demo of how the system behaves in real environment, while the user is carrying Google Pixel XL, which is unseen during the offline phase. The red pin here is the ground truth location, and the person is the estimated location. On the right panel, the mobile camera captures the scene while the user is walking around. It's clear that OmniCells is accurate enough even when tested by unseen phone, as it has provisioned to device heterogeneity. Now, we compare OmniCell's performance to the baseline system, which is the best cellular-based localization system called Cellular. The baseline on the right panel and OmniCells on the left panel. It's clear here that the baseline system is suffering from device heterogeneity problem, leading to a bad user experience due to its large error. In conclusion, we proposed OmniCells, an indoor localization system designed to combat the hardware diversity problem in client devices. OmniCells extract device invariant features, which are a combination of classical and deep learning features. Implementation of OmniCells on different phones showed its consistent performance, which improves upon 5 different state-of-the-art systems. In the future, we plan to investigate the effect of changing the phone placement on the performance. We plan to consider more devices in the testing. We plan to investigate the feasibility of our technique on Wi-Fi or sensor-based localization. Thank you. I would be happy to receive your questions.